Hey programmers, Alvin here. Right now I want to go over a Python solution for this tree value count problem. So we'll jump right in. I think this time around we'll start off with the recursive solution. So we know that this problem has us do a count, which means we need to do some addition, right? And we'll start with our base case. One of our base cases is going to be if our root is none, right? So if root is none, I can treat that as if it's its own top level input. So that kind of means the empty tree. Right, so how many times could I find the target in the empty tree? Well, that's definitely 0 times. So return 0. Cool. Now we're going to need our recursive calls. And I know that I need to call a function, right? I'm going to pass in root left and look for the same target. And same thing for the right-hand side. And what do these calls return? Well, they're going to return to me numbers, and the number represents how many times I can find the target in the left subtree, and also how many times I can find the target in the right subtree. So what I want to do is take the total of those counts, so I'll just add them up, just like this. Cool. And then I need to consider myself. So I need to consider root.val. Notice I haven't accessed root.val yet. And so depending if root.val matches my target, I want to add 1 or not, right? So maybe I'll just use a variable here. I'll say match, and I'll use some Python ternary. So what I can check is, all right, I'll use 1. I'll make match 1 if the root val is equal to the target. Otherwise, I'll make it 0. So this is what a Python ternary looks like if you're unfamiliar. So when the value is equal to the target, matches 1. When the value is not equal to the target, matches 0. And then I can just actually add that value for match into my running total, right? Then from there, I'll just return that final value. Cool, so pretty short code. Let's go ahead and test this for Python. Cool, and there we have our recursive solution for tree value count. While we're here, I'll also, of course, show you maybe an iterative solution. Maybe I'll choose to do the breadth first iterative. So define tree value count once again, takes in the root and the target. And I do believe that in this problem, we could be given an empty tree up top. So does that exist? Yes, it does, right? So sometimes they give us a null, it looks like, right? So like a none pointer. And so I'll need to go ahead and account for that. So if root is none, then I should go ahead and return 0. But then beyond that, I can create my queue. So I'll go ahead and implement this one efficiently right off the bat. So I'll go ahead and I'll say from collections import deck. That way I can, in O of 1 constant time, remove from the front of my queue. So I'll say queue equals deck, and I'll initialize that with the root. Nice, and I can end up with my main code to just iterate and traverse through every node of the tree. So while my queue is not empty, I'll do some logic. I want to remove the front of my queue, so that's queue.popleft. Invoke that. That'll give me my current node. Then from there, I need to have my code to add the children if they exist, right? So if current.left is not none, then what I'll do is add that child into the queue. So queue.append current.left. And that code is pretty symmetric for the right-hand side, right? So if the right exists, do the same thing. Nice. Now we need to be sure to actually accumulate a count, right? So iteratively, it's straightforward. Create some count variables, set it at 0. And whenever something leaves the queue, I think would be the best place to put this. Whenever something leaves the queue, I'll check, all right, if that node's value is equal to my target, then I should count it. So count plus equals 1. And then, of course, after my while loop, after I'm done iterating through all of my nodes, just return the final count. So this would be a one iterative solution you could come up with. I'll give that a test run. See what we get. They both have the same complexity. Nice, and now we saw a recursive and also iterative solution for this. Technically, we implemented this as a breadth first. I'll leave the depth first iterative version to you.